Hello friends, welcome for another image classification project using MLP mixer. So this MLP mixer is used for waste classification. It will classify the different garbage wastes into different categories like e-waste, plastic, glass, organic, etc. So before diving into the implementation of this model, let's go to the discussion of MLP mixer architecture so that we will understand it better. For that, I am going to the notepad to explain the MLP mixer. So we will discuss about MLP mixer. MLP mixture is a pure MLP based vision architecture. It does not use convolution or attention mechanisms. Instead, it solely relies on two kinds of MLP layers to mix spatial and channel information in an image. So what is MLP mixture? MLP mixture is a pure MLP based. Here MLP means nothing but multi-layer perceptron. I hope you know the multi-layer perceptron architecture, and it's nothing but a feed forward network where we will have a dense layer with GALU activation and a dropout layer, that is the multi-layer perceptron, and we will be using the same here. So let's discuss on MLP mixture more. So MLP mixture is a pure MLP based vision architecture which does not depends on convolutions or attentions. Instead, it solely relies on two kinds of MLP layers. MLP mixture will have two MLP layers. One is for mixing spatial information and other MLP for mixing channel information. So with the intro you can understand that MLP mixer contains two mixer blocks. So let's discuss on what are those. So the first one is called token mixing MLP. The token mixing MLP mixes information across patches, that is nothing but spatial mixing. So what it does, it makes information along or across patches, that is nothing but spatial mixing, and it operates along the patch dimension so that spatial mixing can be done per page as input. So operates along the page dimension, which treats features as page as input. Then we will have another MLP which mixes channels, so it is called channel mixing MLP. And the purpose of channel mixing MLP is that it mixes features within each page, that is per location mixing. So what it does, it mixes features within each page, that is per location mixing, and it operates independently for each page along channel dimension. You may be noticing that I am speaking only about MLP, but what is that MLP? So MLP is nothing but it contains one dense layer with some units and GALU activation function. Then it will have a dropout layer with some dropouts. So this is the MLP, and after the token mixing MLP and channel mixing MLP, we will have one more layer, that is normalization layer, which will be used just before MLPs instead of batch normalization, which is does in vision architectures. So we will be using layer normalization just before MLPs instead of batch normalization, which is generally followed used in vision architectures. Then also we will have skip connections around each MLP block for stability. So what we will do, we will have skip connections around each MLP block for stability. So these are the layers in the architecture of MLP mixer. After this, let's discuss on advantages and disadvantages. So advantages of this architecture is, it is very simple architecture. Yes, Here we don't have any more contents or any layers which are complicated. We just have MLP blocks and layer normalizations and then skip connections, not more than this. So it is very simple architecture. Then the second advantage of this is that it scales well with data and it is computationally effective. So scales well with data and computationally effective because we don't have either attention layers or convolution layers. That's why it is computationally effective comparatively to other vision architectures. And disadvantages of this model is that it lacks inductive bias like local connectivity and translational invariance. It lacks inductive bias like local connectivity and translational invariance. Then the second disadvantage is that it requires more data and training time to reach the same performance as CNNs or transformers on small data sets. So what the disadvantage? It requires more data and training time to reach or match the same performance as CNNs or transformers on small data sets. These are some disadvantages of MLP mixtures, and we have some improvements for this architecture to get better results or better performance. And let's discuss what are those improvements. So we can obtain better results by increasing embedding dimensions or increasing the number of mixer blocks or training the model for longer. So can be obtained better results by increasing embedding dimensions, increasing the number of mixer blocks and training the model for longer. These are the some improvement techniques used for MLP mixture. So this is what the architecture and more about MLP mixture. And let's go to the implementation part of this MLP mixture for waste classification. So at first let's import the required libraries like NumPy, TensorFlow, Keras and Matplotlib. NumPy is for numerical calculation, TensorFlow and Keras are for building the model, and Matplotlib is for data visualization. So it will take some time. Yeah, the execution completed. Then as we are using GPU strategy to accelerate our training and speed up the training time, we are using GPU strategy. So to build that strategy, we are having a method mirrored strategy in the TensorFlow library. So we will be using that and building our strategy. So before building that, you have to go to the settings in the Kaggle notebook and select either this GPU T4 into 2 or GPU P100, and make sure you are having that setting in your Kaggle notebook. Let's build the strategy and see the number of cores. So we have 2 cores because we are using GPU T4 into 2. After that, we are generating the train dataset and validation dataset from the custom waste classification dataset available in Kaggle. So you can get that when you add the dataset through this button add input, and I have added this dataset using add input. And you also can upload the dataset if you have the dataset in your local folder. Then I have copied this train path which contains these subdirectories, and from that I have created the datasets. So you also can copy this and create your own datasets. After this, I am using image dataset from directory method to create or generate train dataset and validation dataset, where I have provided the directory path, then subset equal to both, so that it will return both train ds and val ds. Then we have a split of 0.2 for validation purpose. Then we have seed equals to 1337, that is for regeneration purpose of the same dataset. Then we have batch size of 128, so that in each batch we will be having 128 examples. Then we are resizing the images to the size of 128, 128. Then we are shuffling down the dataset. So we will be creating 2 datasets, train ds and validation ds, from this dataset directory available in Kaggle. So this method found 9214 image files belonging to 9 classes, and that classes are e-waste, automobile waste, battery waste, glass waste, light bulbs, metal waste, organic waste, paper waste and plastic waste. And from the 9214 files, we are reserving 7372 files for training and remaining for validation. So let's see the class names available in train dataset. So we have an attribute class names which is applied to the train dataset, which returns the class names available. So these are some class names available in the training dataset. After that, let's see the step of images and labels when we take out one batch from the train dataset. So you can see in each batch we have 128 examples and each image of 3 channels and height and width of 128 pixels, and we have 128 labels in each batch. After that, I am taking out two batches from the trained years and plotting the images from that, and I am only plotting the 16 images with their class names or labels using the matplotlib. So let's do that. And I hope you know this code, so I don't need to explain. If you need, please comment me down in the comment section. So it will take some time. So it is taking some time. Let's rerun it again. Yeah, it came. So you see what happened, why some images are not visible. Let's rerun it again and again. Yes, all images came. So you can see this is a plastic waste, this is a glass waste, e-waste, battery waste, metal waste, e-waste, again e-waste, glass waste, organic waste, metal waste, organic waste, battery waste, again battery waste, paper waste, plastic waste, and metal waste. So we will be building the model from now onwards. Before building model, we are building a small mini sequential model for augmenting the data input given to the model. So in that sequential model, we have a normalization layer, then a random flip, and a random zoom layer. So our image input will pass through this, where first the image is normalized, then randomly flipped, then randomly zoomed. And as we know, the normalization layers should be adapted before proceeding for training the model. We need to adapt this normalization layer. For adapting, we should have the images from training dataset only. That's why we are using map method to take out the images from the training dataset, and using that we are adapting the normalization layer with adapt method and adapting data. So let's adapt the normalization layer and build the sequential model for data augmentation. So it will take some time because it will adapt the normalization layer. Yes, we have built sequential model for data augmentation. Then we have a pages subclassed layer which will take out or extract pages from image and reshapes that pages into a dimension which we will be providing, and these pages will be fed to our MLP models. So for that, here we are getting an argument page size from the user, and we will use 8 pixels as our page size. Then in call method we will do the layer calculations. So at first we will extract the patches from the input image with this page size and save the patches in the variable patches, and then we will get out the batch size from the pages and the number of pages from the pages and the page dimension, that is the number of array items in the channel dimension or the last dimension. Then we will reshape all the pages to the shape of this, that is batch size, number of pages and page dimension. Then I have used getConfig method for serialization and deserialization, but I won't be using this for building a user interface. So if you wish, you can save it or you can delete it, but I am saving for right now so that I will show you the best model from all the train epochs. So let's run this and create a patches subclass layer. Then here comes MLP mixer layer. This is the layer we will be using. So the MLP mixer layer will have two MLP blocks. So this is MLP 1 and this is MLP 2. So we are providing number of pages, hidden units and dropout rate to all the MLP models or layers. So for each MLP model or sub model, we are using a sequential architecture, and in each that we have two dense layers, one with GALU activation, another for linear projection, then a dropout layer with some dropout rate. And for MLP2, again we are using a dense layer with GALU activation function and a dense layer, another dense layer for linear projection and some dropout rate. And one thing you should notice that in the second dense layer of MLP1 we have number of units equal to number of pages, while in MLP2 we have number of units equal to number of hidden units. Then as I told, we will be using a layer normalization just before MLPs. So we are defining a normalization layer here with some epsilon value that is equal to 0.00001, that is 1e minus 6. Then we have build method for building the shapes of our input or generating the weights of layers. Then we have the call method which will do all mathematical calculations. So at first we have the normalization layer which normalizes the inputs. Then we are transposing the normalized inputs to this shape, that is axis equal to 0 to 1. That means we are getting number of batches, number of pages and hidden units, which will be converted to number of batches, hidden units and number of pages. After transposing that, we will apply MLP 1 to that. Then again we will transpose out the outputs from MLP 1, and as we are getting number of batches, hidden units and number of pages, now we will convert it to number of batches, number of pages and hidden units. I have written it hidden dimension, hidden units. So and then we will do a skip connection for stability. So here what we have done, that we have a skip connection with MLP1 outputs with the inputs, and after that we will again apply normalization layer just before the MLP2, and we extract the X patches, or the outputs or normalized values are saved in X patches. Then we provide that to MLP2 on each patch independently. Then we will get MLP2 outputs, and finally we will add both X and MLP2 outputs as a skip connection for stability and return the output X. That is what our MLP mixer layer does. And here I have used getConfig method for serialization and deserialization of number of patches, hidden units and dropout rates. Let's run this cell and build our MLP mixture layer. So we have successfully built a subclass MLP mixer layer. Then we are building a MLP mixer block with MLP mixer layers in a sequential model. So here we will be using the number of patches equals to image size divided by page size to the square of them. So we will get 16 square, that equals to 256 pages. So we are providing 256 number of pages, and hidden units equals to 256 and dropout rate equal to 0.2, and we are iterating the MLP mixture layer for 4 times using a for loop. So this is the MLP mixture block that we will be building. Let's run it. The MLP mixture block is built. So now the model part, that is we will build a MLP mixer model. So at first we will receive the inputs of SEF 128, 128, 3. Then we will augment the inputs. Then we will extract the patches. Then we have a dense layer for linear projection. Then we will apply MLP mixture blocks. After that we will have a global average pooling with 1D layer, because the output of this MLP mixture block will have the shape of this, that is number of pages and hidden units. That's why we are having a global average pooling 1D layer. Then again we have a dropout layer with 20% dropout, and finally we have a dense layer for classification with number of units equal to length of class names array. Then finally we are building a functional model with inputs and outputs. So let's run this. After building the model, we have to compile the model under the strategy scope, because we are using the accelerator for accelerating our training. So we will build and compile our model inside the strategy, and to compile we need a optimizer, a loss, and or a matrix. So we are using Adam W as optimizer with 1e minus 3 learning rate and 1e minus 4 weight decay, and we are using sparse categorical cross entropy loss and sparse categorical accuracy as matrix. Let's compile our model under the strategy, that is GPU. After that, we are training our model with the fit method, providing train dataset, validation dataset, and number of epochs equals to 30, and checkpoints as callback. So our checkpoint is nothing but model checkpoints, which will save the weights of the model after each epoch in the file path MLP underscore mixer.keras. It will monitor the validation sparse categorical accuracy, and if the validation sparse categorical accuracy becomes maximum, then it will save the weights, and to save the weights we have save best only equals to true. That means best weights will only be saved. So let's train our model. It will take some time, and don't worry about the time, I will speed it up, the training part. We are in the 30th epoch, so let's see what will the training loss, training accuracy, validation loss, and validation accuracy. So we got training loss of 1.1154 and training accuracy of 0.6099, validation loss of 1.8855, and validation accuracy of 0.4300. So it can be improved by increasing the number of epochs. As to reduce this runtime, I have used only 30 epochs. You can try for 100 epochs. So let's see the predictions of our model. So for that, I am taking out one batch from validation dataset and predicting levels using model.predict method, passing the batch to this method and saving the output levels in the predicted levels and showing the images of that using AMSO method and showing the level of the image predicted using the title method available in matplotlib library. So let's run this. So here you can see it classified this waste into plastic waste, this is paper waste, this is e-waste, this is battery, this is organic waste, this is metal waste, this is paper waste, automobile waste, battery waste, plastic waste, paper waste, metal waste. So some of the images are misclassified, so don't worry because we are just having a validation accuracy of 0.43. that's why the accuracy is very low. Let's change the input and check. So this is battery waste, correct, this is correct, this is wrong, plastic waste, correct, plastic waste, incorrect, automobile waste, incorrect. Battery waste, correct. Glass waste, correct. Glass waste, correct. Paper waste, correct. Metal waste, maybe this is incorrect. Organic waste, correct. So some are correct and some are incorrect, and let's evaluate our model using the validation dataset. So after evaluation, we are having a loss of 1.88 and accuracy of 0.42, that is 42% accuracy, which can be improved. And let's see the best model we got after 30 epochs. So load that model from the checkpoints and then evaluate the model. So let's load and evaluate the best model from checkpoints. So you can see the loss is 1.78 and the accuracy is 0.45, that means 45% accurate. So using the best model, let's predict the levels for the waste classification images using this same code. Let's run this. So you can see this is plastic waste, paper waste, e-waste, battery waste, organic waste, metal waste, glass waste, e-waste, paper waste, plastic waste, paper waste, glass waste. It is classified somewhat correctly. Let's change the batch. Misclassified to this, and remaining all are correct. After that, let's save the model so that we can use this model building our user interface, so that other users can use our model to predict the waste classifying images level. I'm not going to build the user interface for this model, so if you want, you can build it. And if you want to download the output or checkpoints or models, let's save it so that it will be shown. So this is the checkpoints we are having, and you can download it from the button when you get on clicking 3 dots. You can download from here. Similarly, you can download the model also and use that for your user interface creation. So thank you for listening me patiently. Thank you very much. Have a good day and a great future.